computing the line. Regression and computing the line. That is the part of what we'll do here. And we start a little bit on the thinking of randomness here. But the statistics we do in the next part. We don't do that in this little section here. Now we are going to think about what is the line really. Hopefully you will remember that you met the line previously in your lives. We do consider in this setting the response. Why? So when we say regression analysis, we make it asymmetric. We make a decision on which is x and which is y. Now I sampled height and weight. So in principle, I could actually choose either. The correlation doesn't make a distinction. The correlation is a symmetric thing. But when I start to put in a line, I have to decide, do I want to make the line of one versus the other or the other versus the one? I have to make a decision. And here, I decide that for this application, the most meaningful way of seeing it is that our weight is a function of our heights. I mean, it may not, I mean, both approaches could make sense. I mean, if you took some other ways of seeing it, maybe. I'm just saying both approaches could make sense. We just make a decision of which is relevant to us. And then we move on from there. Now, the way we're going to put it is like this. This is the way we are going to put it into sort of the stochastic framework or the random framework, and the way we are going to try to do and be intelligent about doing statistics finally in looking at this. We are going to consider that the outcomes, that in our case, the weight, is essentially sort of on average its mean relation to x, the height, is a linear function. That's the basic. And then of course, well, what if it's not linear? I spoke about that. Yeah, but then we have extended methods, right? For now, we discussed the linear assumption and the linear. And it's also the mostly used one because it's the most basic way of looking at the relation between two things, is to think that it's linear. I mean, the real world does not consist only of linear relationships, but it's the first step again towards being able to jointly look at two things at the same time, right? And this is a first step course. This is not a course where you make all the steps. On average, y depends on x as a linear function, but we also acknowledge the fact that, of course, it would be naive to have a model or some mathematics that would express height explicitly, that would express weight explicitly as a linear function of height without putting into the way of looking at it that, of course, there is a random variability in our weights that I discussed before. There will be differences for people even of the same height. Even people of the same height will not all of them have exactly the same weight. That is what we put into the random error. The random error epsilon captures the individual deviance, the individual difference away from what the line expresses as an expectation. To emphasize again, we have the linear model. We have some random errors. We also sometimes call them errors. We sometimes call them residuals. There are some words typically used around this. Usually we call y the dependent variable because y depends on x. X is somehow called the independent because the other is the dependent. This is a terminology that can confuse sometimes, but nevertheless, let's introduce it because that's used by people out there. And then, of course, we have the intercept and the slope, the alpha and the beta, the intercept and the slope of the line, something we were taught many years ago to know what is the intercept and what is the slope. And we have, to repeat myself, what is left, the individual deviations from the line, we call it residuals or random error. And of course, just to have a look, we also get back to you again. This is y, this is x, this is the intercept. And just for you to remember, now if this x was 3 and this x is 4 here, I hope you remember what the interpretation of the beta is. namely the change of y when we change x 1 unit, right? That's beta. That's the interpretation. Of course, we're going to use that. I mean, I have to assume that you know that, but now I repeated it. This is the beta is often the thing that is telling us the interesting story when we do regression analysis. So we have to understand what beta is expressing to us. Now in regression analysis, we look at betas instead of looking at means, basically. That's the point here. So the big question, of course, is how do we compute the line? How does R compute the line, and how should we compute the line when we have those points? I believe that many of you will have met this previously. Can you raise a hand, those of you who heard about this before? So a double handful, I guess. Difficult to go through a physics course, I think, for instance, without having to use something like this. Anyway, here are some other observations just to exemplify that there are two different ways that we can have linear regression data. That's why I still have this here, because now we already have two examples. The height-weight example, the plots I just showed you out of the blue. And then these data. In the height-weight example, the x data were also random, but I decided I wanted to see weight as a function of height. That's perfectly valid. But we can also have situations where sort of we decide what the x should be. The x is a part of the designed experiment. It could be time points. I want to observe a system at time point 1, 2, 3, 4, 5. It could be different chemical compounds. You put a dose of 1 into the system, a dose of 2, a dose of 3. You could decide which doses you're using, and then you can measure the sort of the reaction to the different doses. So you may decide on the x's yourself. That is perfectly valid for regression analysis. And we want to find this linear function between x and y. And the big question I already gave is, how the heck are we going to compute the intercept and the slope? And here we use A and B when we are talking about the estimates of alpha and beta. Alpha and beta are sort of maybe the underlying values, and A and B are what we compute. Well, again, now we've seen 3 different ones. How do we compute this line? This is a very precise one, but still we need to find out how to compute it. We compute it, as the title indicates, by the least square method. Let me just... Which one should I take? I'll take this one, since I brought it here. What is the least square method? I didn't use a lot of slides on that. The least square method is the one that minimizes the difference between each observation and the line. You minimize this one. What does that mean? It means that you look at all the vertical, because we are measuring y differences here. It's y differences that we are minimizing. So the least square, minste kvadrater in Danish, least squares method, is taking the square of all of these. In this case, they're quite small, actually. The square of all of these, this one, all the bars there are such, the difference between the observation, which is the dot, and the line. So in a way, it's a mathematical challenge, right? We are searching for some line that sort of makes this term as small as possible. Least squares. We make the sum of the squared differences as small as possible, right? That's a minimization challenge. You would have to minimize a function of 2 variables, because the y's are given, the x's are given, right? These are numbers. We can plug them into this expression, and then this is a function. Mathematically speaking, it's a function of 2 variables, a and b. Let's do a 2-dimensional minimization. I'm not going to do it now. It's a mathematical challenge, right? that you will have seen, I'm sure, in math courses, or will see. Anyway, it has a nice solution. It can be solved, actually. To express exactly what the solution to this is, we usually use some sort of names of different terms here. I mean, we're going to write out a formula now for how do we compute the intercept and the slope. It can be written out. There is a nice mathematical analytical solution to this minimization problem. And it can be spelled out. I mean, let me show it. Here it is. It's not that complicated. There is a way of telling what the solution is to this problem. So it's we don't need, you could say, a computer. We do have a computer. So you can say, we may not need the formula, but still it's the idea of this course, not only to tell you how to do it in R, but also telling you what is behind what R is doing. You are going to be engineers, so you are going to be able to think for yourself also. To express this, what is the formula for the slope estimate, the B? We use these terms, Sxx and Sxy, and of course then I will have to tell you what these are, which were on the previous slide. Sxx is, if you look at it, actually the same as taking the sample variance of x and multiplying it by n minus 1. Can you see? Basically, roughly speaking, it's just the x variance, right? It's the x variance where I don't divide by n minus 1. That's also a way of saying it. So it's the sum of squared deviances. It's the thing you compute if you're going to compute the variance of x, but then you don't divide by n minus 1. And you have the Sxx, the sum of squared x's. Then we have the similar thing, n minus 1 times sy squared. The variance of y, you could say, is in the syy. And then we have the combined thing, which is almost the same as the one we used for the correlation, apart from the scaling, you could say. It's the same core quantity as the one being used for the correlation, namely the sum of cross products, the Sxy, where we take x deviations and multiply by y deviations. This is the sole new thing to be used for regression correlation analysis compared to what you've seen previously, because it's more or less the correlation. You could also say, in fact, that the correlation coefficient is also Sxy divided by the square root of Sxx times Syy. So it's just to say that if you looked at the correlation formula, you would have the standard deviations there also. So these things are connected, obviously. That's the least square method. Having computed the slope by taking, and here is in a way, even though of course it's difficult to know that it should look exactly like this, but somehow it makes sense. If you look at the formula for B, it makes good sense. We take something, Sxy, which measures the covariability or the relation between x and y, and we relate it to how much does x actually deviate or vary. So we sort of measure how different is y related to x conditional on x. That's a slope, right? How much changes y as a function of x. So somehow I think it makes sense. Of course, it's difficult to know that it should be exactly like this, but I think it makes sense. Having computed the slope, it's easy to compute the intercept. The intercept is simply using the slope, making sure that all lines, no matter where they are, lines always go through the average of x, comma average of y. So the line will always pass through this point. And knowing that, I mean, it's easy to find the intercept from the slope and from the two means. I mean, I'm just telling you this. I mean, this is a solution to the mathematical minimization problem that tells me that it goes like this. This is not because I decide myself that this is how it's supposed to be. The solution to the minimization challenge gives me this result. So now I remember it, and knowing that a line will always the least squares line will always pass through the mean of the two. That's a nice thing to remember. That's it basically for the least squares. For the example that I brought, and that's not particularly interesting, but let's actually instead of that, let's have a look at the numbers for our height and weight example. Anyway. X bar, Y bar. Okay. Average height, 185 centimeters from you guys. Average weight, 79 kilos. I could compute the standard deviation of heights. That's like 8-9 centimeters. So plus minus 2 standard deviation is like 17 centimeters. 185 centimeters plus minus 17. We could, I mean, if we should do the correlation by hand, we should use these. Let me instead look at this one. Sum of height minus x bar squared. Sum of height minus x bar squared. This is SXX, right? Taking all the heights, which are the x's, subtracting the mean of the heights, squaring them, and adding all the terms together, right? SXX. SXX for our data is 754.9. Please note that this is the same as taking, I should remember now that I have a sample of 11 and not 10 as last year. This is the same as taking the variance of the heights and multiplying by n minus 1. That was what I told you on the slide. Let's just check. Is that the same? Yes, that's the same. Then I could compute SYY. And in fact, SYY, and here's a new one actually. Here's a new one that you may want to use, you don't have to use it. There is also a cov function. I've showed you a var function. A var function is the variance function. There is a covariance function, because covariance is actually the name of SXY divided by n minus 1, right? And that is why if I take the covariance and multiply by n minus 1, I get SXY. Should we try to see what is SXY? 418. Here is then the formula for the correlation, right? Correlation, that's the one I wrote with my handwritten on my slide from before. And let's finally do different ways. What was it? SXY divided by SXX. This was the slope. Here's the slope. Maybe we should this is the interesting. 0.55. What is the interpretation of 0.55? Before we have a break. This is the slope of I jump back to the height weight example. I computed the slope based on the formula here. B is 0.55. What is the interpretation? Please?
Every time you go 1 centimeter up, you go 1.55 kilos.
0.55, yeah. 1 centimeter, exactly correct. 1 centimeter gives 0.55 kilos on average in your sample, right? 2 centimeters gives 1 kilo. That's the average relationship between weight and height, estimated from your sample, right? That's the interpretation. That could be an interesting number if you did a scientific study of something that you didn't know about. That could be the interesting number to quantify how weight depends on height. 2 centimeters, 1 kilo. We need a break now. But now if we want to do such a thing and do such a claim and say that's how it relates to the population, then we need to do some statistical thinking also. It's not enough just to compute this number. We need to think about what is the uncertainty here, like this whole course has been about. So the last part of this lecture is going to be about how to do statistics on these numbers. Think and do statistics. But let's do our good 15 minutes break by now, so we start again 5 after.